Hi, it's Michael. I wanted to give you the overview of the tools and the technology that we're going to move into as you've started the course. It's pretty human. You're trying to understand exactly how to formulate questions around how to make sense from things. And so now we're going to introduce computers and what they've been doing. And maybe in between, I'm going to kind of get you excited about the tool you're going to use, which is going to be Notebook LM. So to get started, let me show you some ideas first. Idea number one. Many of you, or at least I know for myself, really started to enjoy computers because of computer games. And if you've ever done this, it's called save game. So what you might never have thought of is how do you save a game, right? So here's this path, let's call it that, through some sort of an experience, etc. And along the way, you're going to encounter different things and you're going to have different maybe abilities to pick things up or something like that. Either way. But to save the game actually means that the game needs to know all of those things and then somehow be able to recreate it at will. So, letting that sink in, kind of challenging, I would guess, right? Because you have to know everything that could possibly happen, or you can't save the game. And therefore, the game itself is going to have some limitations to it. And that's just the way things go. Um, but we know, however, that this idea of state, by the way, if you go to any of the services that you probably use quite a bit, it's like you also expect it to save state. You expect Netflix to know kind of how you or what you were just watching or something like that. Like you expect it now that it's going to keep track of what you're doing. And I think what's interesting about that is just only recently have video services start to have profiles so that they realize there's more than one person watching this. So it's sort of like this is an evolving thing. It's actually not simple. And I just want to start here because modeling in the world that we're used to, which is called relational databases. So I'm just going to show you a relational database here, I guess. Yeah, here we go. We start in our earlier class with this idea of data. Data underpins everything. Data is pretty rational. It's really just a name value pair, meaning it's like, here you go. Customer has a first name and a last name and an email. And for some whatever reason, they have two emails. But who knows? You have to really think this through pretty carefully to say, hey, the world that I want to create, this is the basis for this world. And that's why data modeling, in here, we'll call it relational modeling because this is kind of showing that in this weird world, we have customers that I guess had names and emails, and that's fine. Then we have products. Okay, we know what those are. They have names and prices and such. And then the customers interact with the product by ordering the product. And yeah, pretty simple yet kind of complicated when you look at it because this is overly simple, right? Like you can imagine products could have hundreds of values that might describe them. Some of those values might be blank. Same thing with a customer. Like, what happens when you don't know something? So, the idea around this data modeling is to try to fudge it as best you can and be authoritative. And good old computers, if anything, they're really good at like following orders, right? If it's not going to come up with something that isn't there. Until about 2 years ago. And that's why I kind of switched everything in my mind to be fascinated by uh, LLMs. So, in order to understand LLMs, let's just start with a little bit of a video because I think, some of this might be interesting when you look at it. So, let me go ahead and start here.
Hello, everyone. My name is Ryan Gosling. How to Fly asked me to give you a quick introduction on the text-to-text capability of generative AI. So if you're AI curious, AI unknowing, or just AI confused like I was, here's my introduction into the fascinating world of text-to-text generative AI. Can I have a blackboard, please, to help me explain the concept of text-to-text generative AI? Awesome, thanks. So, what are large language models, also known as LLMs? A large language model, or LLM, is a type of artificial intelligence model designed to understand and generate human language. It can execute tasks such as translating languages, composing text, answering questions, writing code, summarizing lengthy documents, generating creative content.
Okay, so I might skip forward a bit because the amusing part of this, of course, is this completely fake Ryan Gosling, who yet is fairly convincing as Ryan Gosling, and that's another fun part of LLMs is how they can pretty accurately manipulate things that we consider to be not easily manipulatable, right? Like you can't really hire Ryan to talk about LLMs. Well, it'd be nice if you could. And weirdly enough, this also gets into our psychology: is why is Ryan talking about this so compelling? I don't know. Maybe we just have an affinity to, well, if Ryan can discuss it, then it might not be hard. This is about a year old, and what was interesting and still is interesting that they were able to get around this is that visual representations within large language models, and that's the weird thing too, is language models can also make images, and it's kind of wild because really all a language model it is, and it is a model, right? You build them, but the building is based on a training algorithm, which is very, very vast and complex, and then it's sort of a distillation. And but inside of a model is really just a bunch of numbers. Actually, that's it. So inside there is no data. There's nothing to look at. There's nothing to unpack. It's really just a bunch of numbers around basically concepts, and that's very hard to get at. But the funny thing about I'm getting back to this is that it doesn't understand what words and lettering are. So this you can see is very misspelled, and it was an early tell. It's gotten better. In fact, it kind of understands how to generate typography that is not misspelled, but it's not a natural thing. And that's what's fun about this technology is we're kind of teaching it as we go along, right? We're sort of what can it do is a big question, and people are very they can worry about it, right? But the nice thing about LLM models is they're practically free. I can open up one right now. I have like a half a dozen, and you can run them on a moderate computer. It's not necessarily fast, and it's not necessarily the best model, but they work fine. So you can get them to, for example, uh, take a dialogue like my dialogue, and you can use it to generate a transcript pretty easily. And that kind of thing used to not be so easy. Speech recognition's been around for a while, but it's pretty good at that, even though it really wasn't trained in doing that. That idea of here's this waveform of my voice and that translates into these vowels. That's what's really fun about LLMs. But let's skip forward a little bit and we get to kind of the meat of what's going on. I will say, actually, this is pretty good because one thing we're going to work with a lot is this idea of a prompt. And a prompt, perhaps you're used to Google, right? Google, if you've used it for a while, you kind of get used to how to prompt Google, and that usually means to be as terse and focused as possible, right? You want to use words that are extremely specific because if you don't, it's pretty good, maybe, at figuring things out, but really it's the context is missing, right? So the more context you give Google, usually it's not worth it. You just want specific words and phrases so that you can kind of hone in, and then you're going to go look at an article or do some sort of venturing off to find the thing that you want. Now, prompts are different. Skip finding things, just say, well, what do you want, what are you trying to achieve? And so the bigger your prompt in LLMs, the more context you're giving this model, which then just goes through, and I'll show you in a minute what it does. But it does work by creating tokens, and tokens are interesting because as I said, the guts of this is just a bunch of numbers, but even then, words aren't even words. They're usually just little bits of like maybe two or three letters. It's fun. Anyway, it's kind of amazing, actually.
Into smaller, more manageable pieces. These pieces is what we call tokens. These tokens could be words, parts of words, or even characters, depending on the model's design. But in most cases, a token equals a word. So in the future, whenever I talk about a token, think of it as a word. Here's how GPT-4 would tokenize our input prompt. Every colored piece of text is a token. So in this example, the model has split the text into 33 tokens. As you can see, a token often equals a word, but when the word is too long, it is often split into several tokens. The next step would be to turn each of these 33 tokens into an embedding, a numerical representation of the complex semantics of a token, so that a computer can fully understand the token or word. So let's pick the token motivate as an example. This can, for example, be turned into the following initial embedding. The numbers in this embedding vector represent the complex semantic properties of a token. 0.95 might represent the likelihood that the token is a verb. 0.87 might represent emotional intensity of a word. Minus 0.45 could relate to the current performance level. And in this way, a huge amount of numbers in every embedding represent the detailed, complex semantics of a word. So where are the values of these initial embeddings coming from? The values of these initial embeddings are based on the parameters received from a pre-trained model. This model has been pre-trained on a huge amount of text coming from books, articles, conversations, movies, etc. By doing so, the model has learned the complexities of the human language.
And I'll just pause there because this is kind of where, as I said, inside of a model, there isn't really anything that you could find, right? It is just, in a sense, all these tokens that have relationships and weights. And by the way, we'll show it. I can actually kind of show it in this way. Whenever you offer yourself up to asking a question, it's going to follow a bunch of paths. And without getting into too much complexity, we can understand that the great thing about, or the interesting thing about this technology is it was designed to run on the processors that were for 3D gaming, which is sort of the same idea. Like you have to create a 3D world. So this NVIDIA would make these game engines, and that was all they were for. And it was because what you needed to do is lots of parallel computations that all come together and make something together, right? So you have to do everything. You don't do it one through at a time. You do them all at once and then correlate it at the end. It's a different kind of architecture. And it was very popular in graphics because that's the kind of thing you don't, one pixel is not it's dependent on each other, but it's more like a cloud, I guess, right? Like so you're seeing that everything has to kind of come together at once. It's a little bit more, if you want to call it, natural computing, because nature also works this way. But when you follow any particular route, that route can be unique, and the more context you give it, the more complex the route. But I'm actually showing this as 2D flat, but it's really in 3 dimensions, and can go in any direction it needs to go, right? That it's just going to follow its weighting. And the real fun of this is that there's a thing called machine learning, which is just to feed lots and lots of data to a model until it's solidified some concept about this is a, for example, this is Ryan Gosling is a pretty solid concept because it's able to not only generate Ryan Gosling, but his voice and other aspects. So that Ryan Gosling model is usually done all through machine learning because you want it to be accurate, right? Ryan Gosling doesn't grow another eye or something, right? Like it's got some very very definite parameters, whereas generative AI can in fact make up stuff because it isn't constrained by the same model. It's constrained by a thing called attention, which is that in a really clever way, it just knows how to ignore a lot of stuff. I guess that's the fun way to put it. But we'll keep going. Um, I think Ryan here, what happens is this is sort of how the model works, and you go into again, it's all just a bunch of numbers. So transforming, let's put it here.
Slightly different meanings and a different importance in a different context. By moving the input embeddings through different transformer layers and by applying what is called a self-attention mechanism, the different embeddings get further fine-tuned to the context, and the importance of each word in the input prompt gets calculated. This process transforms the initial embedding into a context-aware embedding. So once we have our context-aware embedding for each token in the input sentence, it's time to decode all context-aware embeddings into an output. Let's go back to our example.
So what it may have glossed over that is quite remarkable in this is that attention mechanism also has to do with introduction of noise, and noise is just that. It's random stuff. Noise is sort of the reason all this works. So prior we talked about prior to this we talked about machine learning, which is based on understanding something empirically, like it just gets so many examples and it's able to create a model that is pretty robust. And it took a long, long time. LLMs happen to be start with this idea of noise so that it doesn't always follow the right path. And weirdly, in the cosmic sense that the more noise you introduce, the more things actually tend to cohere better. It's a strange thing, but worth exploring if you want to go there. Um, so this randomness is actually really important. I was also going to say the thing here that it's talking about what it was trained upon is, of course, pretty big, but I will say one of the major sources is things like Wikipedia, which is in itself just a huge database that we created based on cooperating with each other. Okay. The second thing is Reddit, very similar. So it really likes very diverse, large, extremely large data sets, especially ones that it considers higher quality. So actually, Reddit is one of the bigger uh, training sources for LLMs. Along with that, there's maybe some books. I mean, the thing is that when people worry about copyrights and such like that, the problem with LLMs is that it gets so it just turns into something else, even though even more interestingly, I can talk to it about our book and it feels as though, and it seems accurate that it has quote unquote read this book. So part of its training, and this I think is Claude, um, that I asked anyway, that it knows what's in the book. So that's good, when you have something that is a fact. But most often it can just sort of now it can go search the web and get some data. It's really more of like a gathering and then distilling into this output token. And before we go on, whenever you add to that output token, meaning you ask it more or recontextualize or keep it going, the entire conversation in its entirety goes back into and also feeds uh, the the traveling and the gathering of tokens. So the more you tell it, unlike Google used to be, I just need to know one word, Ryan Gosling, and it'll come up with what I want. Here it's like, how would Ryan Gosling explain an LLM? Is actually a really interesting thing that LLMs can do. And I think pretty much we're good. Let's see. We've got output token. Oh, we've got temperature. So the idea, often you're not.
It's also very important to highlight that every generation cycle only generates one token at a time based on the embeddings matrix of the input. So let's quickly go back to our example. Based on the embeddings matrix of our input prompt, the first output token might be listen. In the second cycle, the token listen moves to the input prompt. Based on the new input prompt, new embeddings are created for each input token, and based on the new embeddings matrix, a new next token is chosen. For example, the token up. This iterative process goes on until the full speech is written. So let's walk over the process once again, and let's do it a bit in a philosophical and poetic way by comparing the workings of an LLM with generating the story of your life. Let's start at birth. You started with a specific small input or context window, for example, where you are born, who your parents are, etc. If your life would be generated by an LLM, the next moment in your life will be guessed based on your history. Your life story will be written as a continuous iteration of new moments that are generated, and every moment generated will be added to your history. Older models would guess the next moment in your life, based only on the most previous moments. The revolutionary part of the new LLMs like GPT is the transformer architecture with a self-attention mechanism. Due to this architecture, the next
And all it's saying is, much like you as a person, you probably cannot easily recall all these things in your life. But all these things in your life are embedded in everything that you've done. So therefore, you've kind of created your save game as you go along, right? You don't get to undo things that happened, and therefore everything you do that is forward isn't related to everything that was past, but it was related to you right prior to the thing you're doing. And if you're interested in that, that is called Markovian. It's a another concept that's about whether or not we have free will or not. And so, there's a lot of philosophical as well as technological fun to be had in studying LLMs, which is what I've been doing for the past couple of years because I like both of those things. It's pretty fun. So I think we're pretty good in this concept of here's a machine that is really just doing a bunch of math, yet it's having to do it in parallel, meaning it has to explore vast spaces. And in the end, it's trying to build a map of all the possible things that could happen. So in our start, we talked about saving the game. In the game, you have to know everything that could possibly happen. In this model, you don't have to know everything that could possibly happen. Everything that could possibly happen is already embedded in this architecture, at least when it comes to communication, right? It doesn't do anything yet, but talk and make things, give inputs and so on and so forth. And I think as we mature in this space, it's more about how autonomous we're going to let this technology be. And many of you might experience this already. You've seen maybe AI generated television commercials, which are kind of odd, right? Because they're still just television commercials, but you can tell they're odd. Maybe what I find is interesting is the tone can be off, right? You ask a simple question, but you get a extremely complicated answer. So there's still a lot to be done with prompting and continuing a relationship because this technology just gets better or worse the more of a big token window that you create. But it isn't an answer machine, even though it tries to pretend like it's one. It's more of an exploration machine. And what I think is valuable for you guys is that you're going to now use a secondary model, which is called RAG architecture, retrieval augmented generation, to start to build kind of your own search engine. So if we like search engines are good because it's really tiresome to go search through a lot of things, right? Whereas going through and searching through massive corpuses of words, like all of Reddit or all of Wikipedia isn't worthwhile. It's not a good use of your time, but this technology is fine with doing that. And in fact, most of their structures are based on it already. So it does know quite a bit. Let's put it that way. And it's just up to you to try to guide it through the path.